Okay, let me give you a derivation of the dispersion relations. That's the second part. Um, Basically applying the boundary condition. So in a nutshell, we have the magnetic field inside with this is a zeroth order. This is the perturbed term B1. Essentially, this B0, B1. And we from the previous video we derived this and this. I'm going to apply those two boundary conditions, one from the Maxwell's equation, another is coming from the pressure balance. And then we will apply to here, apply those two boundary conditions, ended up with dispersion relations. Just a reminder, we have a c can be expressed in terms of this way, and the phi can be expressed in this way. Both c and phi is proportional to exponential, so like it's a function of z and theta and z in terms of exponential I theta, I am theta plus I k z. And keep in mind that you can think basically inside of the cylindrical plasma we have basically a current, and then from the basic electrodynamic we have B theta equals 2I over CR. I hope I didn't mess up the unit. So first let's try to calculate the N1, basically the perturbed normal unit. So let's look at basically we have the original surface, and after short time period there's a displacement to another surface, to the green surface, with a c change. And let's assume there's a delta r that is lying on the surface, original surface, and we have a delta r prime lying on the perturbed surface. So like the cylindrical surface changes as go with the displaced vector. And we assume that N0 is original normal vector to the original cylinder, and N0 plus N1 is a normal vector for the perturbed surface. So we can write r prime in terms of basically negative c plus r prime plus c. Those two c, one is at the origin like r naught, another is r naught plus delta r, and then this is basically writing the delta r can be expressed in this way, and we can write c r naught plus delta r in terms of this. This is basically the like first order approximation, like from Taylor's theory, and we plug this in here. We end up have delta r equals delta r prime equals delta r plus delta r grad c at r naught. And we know that delta r prime is on the green surface, and the n naught plus n1 is normal to the green surface. Then from this we know that delta r prime dot n naught plus n1 is 0 because they're perpendicular to each other. So we plug in this to here, and this thing to here, and then we know that delta r dot n naught is 0 because they're perpendicular to each other, and delta r grad c n1 is a second order. So we're left with delta r n1 delta r grad c n naught. and that's what we have. If we take the common factor delta r, we're left with this. We know that n naught is basically the as a unit vector of r radius radial unit vector. So we ended up have n1 equals negative grad c r, and this will be used on the this boundary condition. So first, let's study the pressure balance boundary condition. So pressure plus the magnetic pressure is equals outside equals to inside. So if we take the first order, when this has a spatial dependence, and the left hand side doesn't. It's just B naught for the first order, but this has a spatial dependence. That's why we need this extra term, and we know that this P here is 0 because we're in vacuum, and this P1 is 0 for the first order, which have proved on the previous video. So we left with B1 B naught. So this is over 4 pi because B1 B naught and B naught B1. So those are 2. So count it twice, then we have this, and here we have grad B naught. So we know from the left hand side, inside B naught is only a z direction. So we have, this will become B1z B naught, and we know B1z can be expressed as ik B naught cz from here. Then this term will become ik B naught squared cz over 4 pi, and all of the 4 pi and 8 pi will cancels out, so we have this term. We just multiply everything by 4 pi here, so this becomes this, and this we know that we can express in this way, and since we know that phi has radial dependence, radial dependence, theta and z dependence, but B naught only have theta and b. So we have B1 theta, B theta, and grad phi as theta direction can be written as Im over r phi. And a similar argument, we have this is basically B1z ik phi. So this term becomes this, and here we know that B theta can be expressed in terms of this. We can think it's just proportional to 1 over r. Then we can write the grad B square B theta square in turn as a negative 2 B theta square over r and r direction, because it's only dependent on radial location, radius, and then this term becomes this. As you can see, 2 multiplied by 2, and this is 4 pi. So then this becomes 4 pi. So everything multiplied by 4 pi, then all those things cancels out. So we have this expression, and it's evaluated at r equals a. That's a first equation that we will use in the future. And then let's study the boundary condition due to the electromagnetic from the Maxwell's equation. So for ideal MHD, we have MB in equals MB out equals 0, and from that we have for inside we have this is N1, which is negative grad r here, B naught, and we know that is in z direction. So this become BIK, because grad the grad at d direction will become IK, and n naught b1 is n naught is at basic unit vector of r, and then the b1 basically can be expressed as this. Then this multiplied by r direction r hat, then this become IK b naught c r. So as you can see, this hold at any condition. So this doesn't help us any way, and then let's study this case at outside of the cylinder, so the vacuum. So similar idea, we have negative grad r, grad c r, b theta bz, that's a b naught outside, and we have b1r. b1r can be expressed as basically grad phi at r direction. So we have this to here, this becomes d phi dr, and this grad at the theta direction can be expressed as I m over r, and the z direction can be expressed as ik. Then we have this expression, so this become this become this, so and this become this. All of this will be evaluated at r equals to a. So we have equation 1 and equation 2, and the one of the could be non-trivial step, I guess, is just for the Bessel function I kr, you do the derivative as r, you will have basically the function, you have a chain rule, dfkr over dkr over dr. So this give us a k, then this derivative become k f prime. So take that into account, utilize equation 1, equation 2, and you can use this expression for c z, c theta, theta, c r, and phi, and then use this equation 1 and equation 2 to cancel out the c z and phi. Then you will end up having dispersion relations. Basically, it's a function of m. So basically, which mole numbers you're having, Ka. So wave number multiplied by the radius of the cylinder, B. So the field, magnetic field, inside and outside, in the zeros order, and the plasma mass density. So that's the dispersion relations that we ended up having, and in the next video I will talk about this dispersion relation.